All right, hello. So I just got word we've been renewed for a third season. And so we're going to start right into chapter 3. So chapter 3 is going to be a relatively short chapter, just 3 sections. And we're going to be talking all about determinants, which is one of the cooler things we've seen so far because it has some very nice properties. The determinant has some very nice properties, as we'll see. So we've seen one determinant before on a 2x2 matrix. Remember that we had determined that if A was equal to a 2x2 matrix, well, A was invertible if and only if AD minus BC was non-zero. And remember, we actually called this here the determinant of A. So the value of AD minus BC was the determinant of A. So I'll make that. So this here was the determinant, not the determinant, the determinant of A. So I want to start off today because I think this will give us some very good intuition as to why it's going to work when we start looking at matrices of higher order. Actually, as to why this relation being non-zero implies that A is invertible. And so to prove number 2, we're actually going to need number 1. So the way we're going to do this is we're actually just going to row reduce this matrix. And so what I want to do is row reduce this matrix and sort of go through the algorithm like I would be row reducing it to the identity. And so if I was going to row reduce this matrix, well, I would probably do negative C over A row 1 plus row 2, right? Because I want to clear out that C. All right, so after doing this, I get the following matrix. D minus B times C over A. All right, well, I don't like fractions, so maybe I'll just multiply row 2 by A. And notice I get the matrix AD minus BC. Well, I get the following matrix, AB, 0, AD minus BC. So remember, an n by n matrix A is invertible if and only if A is row equivalent to IN. So let's go over some possibilities of what could happen with this partially row reduced matrix. Well, if AD minus BC is non-zero, we can turn this into a 1 and then use that 1 to clear out the B, turn this A into a 1, and we've got the 2x2 identity matrix, right? So if I get a non-zero entry here, then all paths are clear to finishing off row reducing that to the identity. But notice if AD minus BC is 0, then I get an all 0 row here, and there's just no way to salvage being able to reduce that to the identity. And so this here shows that by 1, we get 2. And so this is where number 2 comes from, is that, we sort of row reduce this, look at this term which has to be non-zero in order for A to row reduce to the identity, and then we can go back and use our invertible matrix theorem in order to say, well, it's only going to be invertible if it reduces to the identity. So what I want to do now is look at sort of the same thing, but for a 3x3 matrix. And so we're going to try and write out what a general 3x3 matrix will look like. And so to do this, we're going to let A equal the following matrix. And we're going to index each entry by row, then column. So notice here, the first entry of each of these A's here represents its corresponding rows. So this is A11, A21, A31, A12, A22, A32, A13, A23, A33. And so we want to do something very similar to this matrix, which we did to our 2 by 2 matrix. So what that means is we want to row reduce this. And now you'll sort of have to trust me on this. The row reduction for this is possible. You'd do it much in the same way. You'd add linear combinations of this row to clear out these values here. Then you'd clear out this. I don't think it's extremely important that we do it. It's a lot of work for, I guess, not a lot of extra information learned. So if we were to row reduce this, and I'll just put row reduce. And if you agree to say that we row reduced it, I'm happy too. We get the following matrix. So we used A11 to clear out the column underneath it. Row 1 really hasn't changed. In doing so, and by multiplying by the right constants, we get that it actually row reduces here. So row reduces to this matrix, where row 1 is unchanged. Row 2, I've got 0, A11 times A21, minus A12 times A21. Then in the third entry of the second row, I've got A11 times A23, minus A13 times A121. In the third row, I've got 0, 0, A11 times delta. All right, so I've got a delta there. Why is that? Well, this is delta. And this is partially why I didn't want to do this row reduction. Delta is equal to A11, A22, A33, minus A11, A23, A32, plus A12, A23, A31, minus A12, A21, A33, plus A13, A21, A32, minus A13, A22, A31. So maybe after looking at delta, you can see why I did not want to row reduce this. But this is this term here. So it's A11 times this. So much like the 2 by 2 case, if A is invertible, then delta has to be not equal to 0. And so in this case, it's a little more complicated, right? There are a few more things we'd need to hold, or we'd need to make sure hold before we could show this goes in the other direction. But we know if A is going to be invertible, then delta has to be some non-zero value, right? Because if delta is 0, I get this row of all zeros after row reducing, and that's what we don't want. So if A is invertible, then delta is non-zero. And so it turns out that the determinant of A, if A is a 3 by 3 matrix, is equal to delta. And so much like the 2 by 2 case, we get this nice property that if this 3 by 3 matrix is going to be invertible, then its determinant, which is this, has to be non-zero. All right, so I claim that we can look at delta in a much simpler sort of way. Because this doesn't give us much intuition, and we're going to learn some really nice property about the determinant that it turns out, by doing a little bit of simplification on delta, we can actually rewrite this as the sum of a bunch of smaller determinants. And so in this way, we're going to show in this section and the next section that we can define the determinant recursively. So that means we can define the determinant of an n by n matrix in terms of a bunch of determinants of smaller matrices. So how do we do that? Well, let's group the following three collection of terms together. So notice for a second, here the leading term of each of these two terms is the same, right? So here I've got A11 as a leading term. So maybe I'll factor A11 out. But if I look at A22 times A33 minus A23 times A32, that looks suspiciously like the determinant of the matrix A22, A23, A32, A33. Right? Because this would be A22 times A33 minus A23 times A32, and then we multiply it all by A11. Okay, let's look at the next group of terms. Well, this looks an awful lot like I can factor out A12. I'm going to do something a little weird here. I'm going to, and you'll see why in a second, I'm going to write this instead as the following matrix, where I have the determinant of A21, A23, and then A31, and A33. So notice for the second term, I could have written it as A11 times the determinant of this plus A12 times the determinant of this matrix flipped around. But what I did is I multiplied these terms by -1 to flip everything. And so if you calculate this out and distribute this -1 through, you do get this collection of terms here. But there's a very good reason why I wrote it out like this, and we'll see in a second. And so we can do the same thing with the last term, where we factor out the A13, and then multiply it by the determinant of this 2 by 2 matrix. A21, A22, A31, and A32. And so notice what I've done is I've written now delta, the determinant of a 3 by 3 matrix, as a combination of determinants of 2 by 2 matrices using all entries from A. But we can actually go a step further than that. So to do that, I need to define a new definition, and then we'll show that this definition nicely aligns with the way I've now defined this determinant of a 3 by 3 matrix. So if A is an n by n square matrix, then the submatrix A sub ij, so this is a submatrix, meaning this is going to be a smaller matrix that pulls elements from A, is the matrix obtained from A by deleting row I and column J. All right, so why is this important? Well, let's once again try to simplify our definition of delta here. And so just for added reminder, we'll remember that delta is equal to the determinant of A, where here A is a 3 by 3 matrix, any 3 by 3 matrix. All right, so here I want to, once again, one more time, simplify the definition of delta. So we're not going to do anything with the A11. Here, I've got the determinant of A22, A23, A32, A33. So now I want to ask, what happens if I delete column 1 and row 1 from A? What matrix do I get? Let's see if I can do that. Well, notice I get this exact matrix here. So this is actually equal to A11 times the determinant of the submatrix A11. And maybe you see what's coming now, minus A12. And so this is why I defined this term the way I did. Because notice this is the submatrix. If I delete row 1 and column 2, I'm left with A21, A31, A23, A33. So A21 times the determinant of the submatrix A12. And finally, if I delete row 3 or column 3 and row 1, I'm left with that matrix there. And so this is equal to A13 times the determinant of A13. And so this will be our official definition of the determinant of A. Well, all of these are the determinant of A, but this is the main way which we will think of when defining the determinant of A. And so this is actually the sort of way we want to think about what the determinant of a 3 by 3 matrix is. So this is really cool. I love when this stuff happens in math because, you know, we just get this nice symmetry here where basically what we're doing is we're working our way across the top row, pulling out A11 and deleting its row and column, multiplying by the determinant of that submatrix, subtracting A12, deleting its row and column, multiplying by the determinant of that submatrix, then deleting A13, or taking A13, deleting its row and column, and multiplying by the determinant of that submatrix. Really cool stuff. And again, A is invertible, or if A is invertible, then this relation here is non-zero. So one way to check, is A invertible? Check its determinant. So I just want to finish calculating this for a 3 by 3 matrix. There are 2 of these on your worksheet. And so I'm going to do the first one, matrix A, on the worksheet, and I will leave the second one for you for practice. So we want to calculate determinant of A if A is equal to the following matrix. 3, 0, 4, 2, 3, 2, 3, 0, 4, 2, 3, 2, 0, 5, negative 1. All right, so what we're going to do is just actually follow the exact sort of outline of the definition. So I'm going to start by taking this 3, and then I want to multiply by the determinant of 3, 2, 5, negative 1. All right, then I'm going to subtract 0 times the determinant of 2, 0, 2, negative 1. So notice here, second part I deleted row 1, deleted column 2, and I take that submatrix. Here I deleted row 1, column 1, and I took that submatrix. Now plus 4 times the determinant of 2, 3, 0, 5. And so what's so nice about this? Well, for one, I get a 0 term here. So this whole term is just going to immediately cancel out. And I know how to calculate the determinant of a 2 by 2 matrix. So this is equal to 3 times negative 1 minus 2 times 5 minus 0 plus 4 times 2 times 5 minus 0. So this is equal to 3 times negative 13 plus 4 times 10, which is equal to 40 minus 39, which is equal to 1. And so that's the determinant of a 3 by 3 matrix.